All right, so a week from today we have exam 1. And we'll see where we get today for topics. It probably won't be all of it won't be, related to all of the problems in strain and constitutive relationship, but probably most of it. So somewhere in the strain problems and everything before that. So let's do this. Whatever, I'll put this on D2L2, but whatever I assign today, that's going to be the last stuff that's relevant for the test. Okay. And Monday and Wednesday, if you have any homework questions related to the test, I'd be happy to answer those. So bring them. Anybody have any homework questions today?
When we do that 6x6 multiplication,
yeah.
So we just make up a program for that?
Yes, you should definitely make up a program for that. So if you have trouble translating like the code, there is code for it for an 89, for a TI-89, but if you have trouble converting that for your calculator, just come talk to me and we can figure it out.
I know on number 6, or at least when you're doing the function problem, like the last one where you're stretching it.
Yeah.
How do you, for 3D objects, how do you determine what's the x, y, y?
Okay, I'm going to do an example like that. So let me just do this example when I get to it. All right, so last time, the big thing, the most important thing probably that we talked about last time were the 4 big assumptions that we make in this class. So the 4 assumptions throughout this class. Are small strains, small deformations, a linear stress-strain relationship, homogeneous materials, and isotropic materials. And isotropic means that no matter how the material is oriented compared to your coordinate system, the material behaviors are the same. Okay, so any direction, the material behaviors are the same. The material's no weaker or stronger along one axis than another axis. And with these 4 assumptions, we get this constitutive relationship between stress and strain. That says the Voigt strain is equal to this compliance matrix that is, so the Voigt strain is, a 6x1. And that's equal to this compliance matrix that's 1 over E, negative nu over E, negative nu over E, 0, 0, 0. And then keep moving the 1 over E along. And then for the last 3 rows, the thing that moves along is just this 2 times the quantity 1 plus nu over E. And you multiply that by the Voigt stress. Okay, so all 4 of those requirements are necessary in order to have this relationship. If you multiply this out, so remember that the Voigt, maybe I should have just put this in that equation above, but the Voigt strain is XX, YY, ZZ, and then the shear strains are represented with that gamma, and we have YZ, XZ, and XY. For the shear strain, for the shear strains, you have to use these different variables. These gammas are different than those epsilons because this is sort of a pain, but there's another way to measure strain that you call epsilons. So the way we're doing it is this. Okay, has to be that. With stress, though, there's a little wiggle room. So the Voigt stress is sigma XX, sigma YY, ZZ. And then you can write it, keep writing sigmas. So YZ, XZ, XY. And that means the exact same thing as, so the first 3 are still sigmas. But the shear stresses are often written as taus. Okay. So these mean the same thing. These, if you write those as epsilons, it means something different. Okay. Well, what does this mean if you multiply this matrix out? So if you multiply the compliance matrix to the Voigt stress, these are the relationships you get. EXX is equal to 1 over E times sigma XX minus nu over E times sigma YY minus nu over E times sigma ZZ, and nothing else. EYY is negative nu over E times sigma XX plus 1 over E times sigma YY minus nu over E times sigma ZZ. And EZZ is negative nu over E sigma XX minus nu over E times sigma YY plus 1 over E times sigma ZZ. Okay, so those are the first, so we have 6 of these equations that come from that one single matrix equation. These first 3 tell us that normal strains depend on all the normal stresses. Physically, does that make sense? So that's saying if you're measuring, say, the deformation along the x-axis, does it make sense that that is affected by not just the loading along the x-axis, but also the loading along the y and z-axis? What that's including there is that bulging slash contracting effect that I was talking about. If you stretch something, it gets skinnier. If you compress something, it bulges out on the sides. Okay, so it's that Poisson's effect. That's what you measure with the Poisson's ratio. So if you're measuring the deformation in this direction, okay, and you compress it down in this direction, the deformation is going to be affected. Okay, so that's true for along every axis for normal strains. Okay. Now what about the shear strains? So if you're measuring the YZ shear strain, that only depends on one shear stress, only the associated one. So this is equal to 2 times the quantity 1 plus nu over E times tau YZ. Okay, so there's no equivalent thing to the Poisson's effect for shear stresses and strains. The XZ shear strain is equal to 2 times the quantity 1 plus nu over E tau XZ. And no, XY is equal to 2 times the quantity 1 plus nu over E times tau XY. So the shear strains is only affected by the associated shear stress. Okay, this is sort of the first glimpse, well, one of the first glimpses of, so the way that we're doing this class mathematically, we're going to do all the same calculations that you would do in the textbook and that the traditional way that you do the calculations in this class. So we'll be able to calculate all the same stuff. But traditionally, everything is just done as scalar equations. And so instead of doing things in terms of matrices and stuff, you're just given these 6 equations, okay? And then when we get to stress transformations, you'll have all these different equations where it's not super clear where the things come from. But to me, it makes a million times more sense to see like where these equations come from. It comes from that matrix relationship. So yeah, this is a place where if you look at a textbook, like the textbook they use at the U or whatever, you'd see these equations instead of that, we're going to do everything this way. But it's nice to see the dependence of the individual values. All right, so let's do an example problem with a tensile test. So let's say we have this material sample. So say, this is like some new alloy of metal or something, and we want to take a measurement to measure the relationship between the stress and the strain. So let's say that on each end we put 5,000 newtons of force. So we put this thing into 5,000 newtons of tension. And we're going to use a coordinate system. For this, we'll always use a coordinate system where the x-axis is along the long axis. Other than that, it doesn't matter which way the axes point. So let's call this x, this y, and this z. And before the deformation, the length is 0.1 meters, so 10 centimeters. And the thickness is 1 centimeter, so 0.01 meters. And the width of the side is 2 centimeters, so 0.02 meters. Let me move that over. Okay. And if you apply this force and then very carefully measure the changes in those side lengths, we get that under the load, when the load is applied, the lengths, I guess I'm calling this lowercase l, so L becomes 0.10003. And I'm going to call this the width, W. Since we're stretching along the x-axis, along the y-axis, it's going to get smaller. So this is 0.00, and then 4 nines and a 2. And by the way, so the way I have it set up in this is that we're measuring the change in length of that thickness, okay? But because it's isotropic and this thing has the same material properties in every direction, we could have instead measured that width and we'd get the exact same answers, okay? So it doesn't matter which one of these two out-of-axis measurements you take, you'll get the same answer for E and Poisson's ratio. Okay, question?
I'm assuming that this is like a small cross section, so the whole thing stretches evenly?
Yeah, so really you would, so if you're going to take this measurement, the way you would do it is you would put little notches or some kind of measuring device somewhere in the middle. So toward the ends, and this will be something we'll talk about later. Towards the ends, you can get things can be a little unpredictable as the forces sort of even out or whatever. But once you get away from the ends, it all is pretty uniform. So as long as you're not near the ends, it's reasonable to assume that it's not going to do anything funky. Okay. And so we want to do this. First, we want to find the compliance matrix. And then second, if this material, this type of material, what we're testing, has a stress tensor at some point of 2 times 10 to the 7th, negative 1 times 10 to the 7th, 0, negative 1 times 10 to the 7th, 0, 0, and then 0, 0, 8 times 10 to the 6. And this is pascals. What's the strain? So the idea here is we're going to do this one very simple test with one piece of, say you do this for steel. So you do this test for your particular composition of steel, and you get some numbers that let you fill in the compliance matrix. And then later, you do calculations for the piece of steel that you have holding up a part of a building or whatever. It's a totally different shape, totally different loads, okay? And if you calculate that that's going to be the stress, now you can use the compliance matrix you got from this simple test to calculate what the strain is going to be, to approximate what the deformation is going to be. Okay, so that's what we're doing here. There doesn't have to be any relationship between the shape or the loading of this and the shape or the loading of that, as long as it's the same material. All right, so for part A, the XX stress is 5,000 divided by the cross-sectional area. So the cross-sectional area here is the 1 centimeter times the 2 centimeters. Are you with me on that? We're talking about this area here. Okay. So 5,000 divided by 0.01 times 0.02, and you get a value of definitely something. 83.3 repeating times 10 to the 9th. I'm using the right stuff. What did you get? Oh, okay. Okay, yes. 2.5 times 10 to the 7th pascals. And then we'll measure the strain along the x-axis, the normal strain. And that is the deformed length of 0.1, 1, 2, 3 zeros and a 3 minus 0.1 divided by 0.1 and you get 3.0 times 10 to the minus 4, and that's unitless. And then in the y direction, EYY is the deformed thickness, which is 0.00, then 4 nines and a 2, minus 0.01 divided by 0.01, and you get negative 8.0 times 10 to the minus 5th. So then Young's modulus is sigma xx over exx, so 2.5 times 10 to the 7th pascals divided by 3.0 times 10 to the minus 4, and you get an E value of 83.3 repeating times 10 to the 9 pascals, 83.3 repeating gigapascals. And the Poisson's ratio is negative out of axis strain. So that's the 8.0 times 10 to the minus 5th divided by, and we have a negative here, divided by the in-axis strain of 3.0 times 10 to the minus 4. The negatives cancel out, and you get a positive Poisson's ratio. You always need to get something between 0 and 0.5, and in this case, it's 0.26 repeating, and that's unitless. And now that we have E and nu, we can fill out the compliance matrix that represents this, our type of, well, this wouldn't be steel, by the way. Steel would have a value of about 200 gigapascals. This is a softer metal. That's not too far off, like copper. But so now that we have that for copper, we can fill out the compliance matrix, and then we can use that for whatever we shape this copper into, you know, make it into thin tube things or make it into a big chunk. This compliance matrix will represent it no matter what. So the compliance matrix with these values is 1.2 times 10 to the minus 11, negative 3.2 times 10 to the minus 12, negative 3.2 times 10 to the minus 12, and then 0, 0, 0. And then just keep moving the 1.2 times 10 to the minus 11 along. and then 0 in the shear spots. So now we're done with those normal stresses, those normal rows. So the next three all have zeros in the normal spots. And then 3.05 times 10 to the minus 11 that keeps moving down diagonally. And the units are 1 over pascals, the way I have it. And you do need to keep track of those units because it's really easy to mismatch your units, and then you're off by usually at least a factor of 1,000. And if you're off on a calculation by a factor of 1,000 or more, your calculations are not very good.
Is an okay way to tell the units by, like, if it's a really, really small number for a really big number, like, would that be an okay way to tell?
Not the units. That's an okay way to tell whether it's a compliance or a stiffness matrix, but the way to tell the units is just to look at what you're using here. We calculated this stress in pascals. This is unitless, and that means that E has to be in pascals, and that means that the compliance matrix is 1 over pascals. Any questions yet? Okay, so now we're going to part B. And we have this stress tensor. So now a whole different part of the company has formed hollow tubes out of this type of copper, or whatever it is. And it's under some loads, and they calculate that those loads at some point in the material are producing a stress of 2 times 10 to the 7, negative 1 times 10 to the 7, 0, negative 1 times 10 to the 7, 0, 0, and 0, 0, and positive 8 times 10 to the 6 in pascals. Well, in order to figure out the strain, we need the Voigt stress. So this stress tensor in Voigt form is 2 times 10 to the 7, 0, 8 times 10 to the 6, and then YZ, XZ, XY. And now to calculate the strain, we're just going to multiply that compliance matrix by the Voigt stress. And what you get in this case is 0.30214. So that's the XX normal strain. Then the second one is negative 0.40896. Then the ZZ normal strain is 0.40, and then 32, and then 0, 0, negative 3 zeros, and then 304. Does it make sense that we have a zero value, that we could have a zero value for the YY normal stress and a non-zero value for the YY normal strain? Yeah, it's because of that Poisson's effect. Okay, it's because these normal strains are dependent on every normal stress, not just the associated one. Okay, but that's not true with the shear strains, and so that's why you see the places where we have zero shear stress, we also have zero shear strain. And so at this point, we have elongation along the x-axis. Okay, it's stretching along the x-axis. We have contraction along the y-axis, elongation along the z-axis. Now the angle between the y and the positive y face and the positive z face stays the same. That angle stays the same. Between the x face and the z face, positive, stays the same. And between the positive x and the positive y face, we have a negative shear strain, so it's getting more obtuse, okay? So you could sketch that out and get a sense for like, okay, it's bigger this way, smaller this way, bent this way, okay? Okay, we have this at one point out of a whole copper tube. So how many more points do we have to do this to represent the whole tube? We've gotten one taken care of, but there's infinitely many points. So we haven't really gotten any closer. So anyways, you just remember that this represents a single point, okay? And if you want to represent the whole thing, you need to represent these functionally somehow, you know, come up with functions to see how these values are varying. Dallas, you have a question?
Sorry.
Okay.
So like this second part B, that's not in relation to the stretching on
Right.
Okay.
That's right. It's a totally different, yeah, in a different country or whatever, they're doing this. We sent them our values for E and nu, and then based on that, they can do whatever they want with that metal and use that compliance matrix. Yep.
Coordinate system that you gave us, that applies to all problems.
For the tensile tests, that's the way to probably do it, yeah. I mean, you don't have to do it that way. You could do it in any coordinate system, but it's sort of easier to do it the same every time.
Okay. Because, so you always want to measure the length of it plus just the little width.
Yeah.
Okay.
Yeah.
So then the subscripts for those, for the equations, they don't really matter too much.
Right, it doesn't have to be those subscripts, it just has to be the axis that's being stretched versus some axis that's not, you know, that's perpendicular to that.
You're not doing this exact thing, you just set the x-axis in the direction of like longitudinal.
So for the tensile test, people normally take the x-axis to be along the loading axis.
Right, yeah.
Okay, but outside of the tensile test, it doesn't matter what coordinate system you use. The Young's modulus and the Poisson's ratio hold no matter what crazy, you know, no matter what the shape of the thing is and no matter where you put your axes.
Just for the homework, it was the Z and the Y is split.
Mm-hmm.
I just thought it was kind of.
Yeah, right. So all that matters is loading versus not loaded for the tensile test. But I always put my x-axis along the loading axis. Any other questions right now? Okay, so now the last thing I want to do today is talk about the rest of the tensile test. So normally you continue stretching the sample material until it breaks, until it breaks into two pieces. Breaks in two. And so if you plot out the XX stress versus the XX strain, so let's plot sigma XX versus EXX. And here's what it looks like. So this is the normal stress along the loaded axis. And this is the normal strain along the loaded axis. Before you load it at all, there's no deformation. And then as you increase the normal stress, as you apply bigger and bigger forces, you get a very nearly linear relationship between stress and strain up to this point. What are these named? I'll call this A. Okay. And then after that, it stops being as linear. So it starts to do something like that. Then you get a little region like this, and then it starts getting stiffer again, and then here's where it fails. From 0 to A is the linear elastic region of this graph. Okay, this is the region where you're going to measure Poisson's ratio and Young's modulus. So you're going to measure E and nu here. And this is also the only place that your compliance matrix is useful. So you can think of that represents the size of deformation where the compliance matrix is a useful thing for which that compliance matrix is useful. After A, it's funny, it tends to be right about at that point A where two different things happen, okay? And there's no reason that they have to happen at exactly the same spot, but it's close enough that we're just going to treat it like they happen at the same place. Two things happen. The stress strain becomes nonlinear. So you can't use that matrix relationship anymore. And deformations become permanent. Okay, so for deformations up to this size, you can load it as much as you want up here. When you let go of that force, it returns back to its original shape. Okay, but right around here, when you hit the end of that linear elastic region, if you stretch it past that point and let go, it's going to be longer than it was. It's going to have a permanent deformation. So this region here is what we care about in this class. That's not to say that after there's permanent deformation, you know, there's no use anymore for engineers. There is, but in this class, we're just not dealing with that. And for the most part, the elastic region is the more useful region for engineering applications. Obviously, like if you're doing research on car collisions or something, then what matters is this nonlinear region, you know, because you want to know what's going to happen after these big deformations happen. But most of the time, like if you're building structures, you're building them in a way that you're hoping they're not going to leave the elastic region, and so this is what you care about. That point A is called the yield stress. And yeah, that point is the failure point. Anybody have any questions about this? Okay, let's stop there.